Good morning, all. In today's session, let us discuss the next concept in your electromagnetics, the first module. Just let me recall what all we have covered. I'm sorry I did not change the sheet. By the next session, I will change it. The first topic which we dealt is experimental law of Coulomb. We have seen what was the experimental setup, that is the torsion balance experiment. Then what was his conclusion, statement, and the equation for force, Coulomb's law of force. We have expressed the Coulomb's law in vector form as well. And as a note here, what I have given, two forces we have calculated, F12 and F21. You should know in both ways how to calculate the forces. Both these forces are opposite in direction. Magnitude wise, they are equal. Then we went for electric field intensity. We have defined what is electric field intensity. Just by doing some modifications in the Coulomb's law of force, F, we have arrived at E is equal to just a test charge Qt, we have taken it is equal to 1. So out of the Coulomb's law Q1 and Q2, Q2 will be replaced with Qt and Qt is equal to 1. So F by Q will give you the electric field intensity. And we have even seen how to find the direction of the unit vector for both positive and negative charges. Then we have come across how to find the electric field intensity in vector form. These vector forms are very important. Remember, I'm referring some 2 to 3 textbooks for all these, whatever I'm giving you these slides. So don't worry, I am referring your prescribed textbook only. Then field due to many charges, we have seen with this figure, if two charges are there in the vicinity of electric field, how to find the electric field? It will be the vector sum of two fields, and we have extended this discussion for n number of charges. Till this we had concluded in the last session. Let us today take the next concept, that is, according to your syllabus, it is volume charge distribution. Okay, directly the title is given to you. The concept name is volume charge distribution. I think in your physics concepts, you might have studied what is a charge distribution or what is a charge density. Okay, but let me just recall all those. You might have forgotten. Before going for the actual concept, volume charge distribution, let us see what is a charge distribution first of all. Then we will go into that particular volume charge distribution. Just let me see some chat box. Okay, fine. So let us go to the charge distribution concept. The word continuous, it means we don't have any breaks in between. Okay, till now the whatever the force or the electric field intensity equations we have got, for all those we have considered 1 point charge, 2 point charge, like that, spaced in a in 3-dimensional space we have put them. Just like imagine a classroom filled with the charges. Okay, so we have imagined, we have found out the expression for force and electric field intensity, assuming these charges spread out in a space. Now, coming to this continuous distribution, what does that mean? If there are number of charges in the space, they are infinite. Okay, we have got many charges spreaded in the space, and they have got some limited dimensions. Okay, till now we have considered point charge. Point charge is what? It is having no dimensions, just a point. And the distance of separation between the individual charges, it tend to become 0, means they are very much compact. Okay, till now here and there we have seen the charges spread in the space, and we have found the electric field intensity and the force. But while coming to the continuous distribution of charges, we say that there are infinite number of charges spread in the space. How they are spreaded? They are spread in the space such that they're having limited dimensions. Of course, point charges we have to consider, and they are very much compact in nature. The spacing between the charges is equal to nil. It is it is tend to become 0. That is tending to become 0. when this is the condition, if this condition exists, we say that the continuous distribution of charges exist. Okay, let me just try to make you understand. If there is three-dimensional space, assume it is your classroom, there are many charges spreaded. Here I am showing you positive signs. You can take negative also, okay, just to show you very much compact charges kept in the space. I am showing you with the help of positive charges. Okay, they are very much compact in nature. There are infinite number of charges, and the distance between these charges, it is tend to become zero. Then we say that it is the continuous distribution of charges. So with this concept, let us see what is charge density. You might have studied this already. What is a charge density? It is generally a charge divided by whatever parameter you are considering. For example, if you are finding volume charge density, it will be charge by volume. If you are finding surface charge density, it will be charge divided by the area of that surface. And if you are finding for the line charge density, it will be the charge divided by the length of that line. So there are three different charge densities that exist. So we will first show we will first see what are these charge densities, and then we will go for the your prescribed concept. Okay, uh, let a charge q coulombs be uniformly and continuously distributed throughout a volume. See, q coulombs of charge means there is not only one charge. Okay, q number of coulombs, there are many charges in the space. Okay, they are spreaded out. Sorry, it's very difficult to drag the mouse. So in the three-dimensional space, okay, in certain volume, okay, assume that this is one volume, a cube I'm showing you. Okay, in that many charges are there. They are very much tightly bound. Okay, very spacing is very less. It is tending to zero, very much compact, solid. You imagine how the molecular structure of solid appears. Like that, they are tightly bound. The distance between those charges, they are tending to zero. If this is the scenario, and assume that how many charges exist, they are q coulombs of charges. Q is not one charge. Q is the total amount of charges. It is q coulombs of charge. Okay, then it is uniformly distributed and it is continuous distribution. Okay, and it is continuously distributed throughout some volume v. Just now I have shown you the q. Okay, so it is v. Then how you define volume charge density? It is charge per unit volume. That is, the charge density is denoted as rho. Okay, if it is volume, the suffix is v. If it is a surface, suffix is s. If it is linear line charge, suffix is l. So rho is the charge density. Hence rho v indicates volume charge density. It is given by the charge per unit volume, q divided by v. Now coming to our concept, if the distribution is not uniform, okay, in generally I am telling, they are distributed uniformly considering q coulombs. Okay, if it is not uniform, then instead of writing this, we will write the space, the within the space, the volume is tending to zero and charges are very much in what? They are very much compact, so that volume is tending to zero. Okay, then delta q by delta v. What is delta? Delta is a smaller value. If the distribution is not uniform, we will consider a smaller amount of charge to the smaller amount of volume. Whenever there is non-uniform distribution, we go for this. And the unit is coulomb per meter cube. Charge is q, volume is v, coulomb per meter cube. So the way we have defined volume charge density, let us see how surface charge density is defined. Again, we consider this q coulombs of charge uniformly and continuously distributed throughout, not volume, In this case, it is over a surface. Some surface we are considering. And a surface, I have not written here, you can take yes. Okay. Then how you define surface charge density? It is defined as the amount of charges that present on that particular area per unit area of the surface. That is rho s is equal to q by s. And again, if the distribution is not uniform, then smaller value we will consider delta q by delta s. It's a general tendency, okay? Even you might have seen in your integrations, if some concept has to be applied to a broader area, first we will consider a smaller part, we will apply the concept there. Then for throughout the area, we go for integration. Then we get overall value. The same thing is happening here. If it is non-uniform, for smaller cases we consider, and further the same can be extended to the entire volume or entire surface. Then let us see what is line charge density. For line charge density, again we have a long conductor. Assume that we have a wire of some length. Then assume if this is your wire, hope it is looking like wire, and this is the thickness of the wire, this is the length of the wire, and the wire is such that the area of cross section, this one thickness, it is very small in comparison with the length is far bigger value compared to its thickness. If this is the case, then linear charge density is the charge per unit length. Rho L is equal to Q by L. L is not, L is the length of the wire. But however, if the distribution is again not uniform, we will apply the concept to a smaller value. Then we will integrate the complete term to get the whole value. You can see here below figures, 3 figures I have drawn. This is one wire length, positive signs, they are indicating the charge distribution. Assume they should be very much compact. Still I would have done it very tightly bound. I have left some space in between. Don't do that. You have to tightly draw the charges distributed. And if this is your overall length, I'm talking about non-uniform. If this is your overall length, then only for smaller part, I will apply the concept of charge density. Then I will get delta Q by delta L. Now, if I want for the complete length, simply integrate it. Then I will get the line charge density for overall wire. Similarly, there is one sheet here, some surface is considered over which a smaller part of the area, delta A, is considered. Here, what is the surface charge density? It is delta Q by delta A or delta S. I think it is S here. You have taken S. So you take this delta S, okay? Delta S. Then if you want for a complete sheet, integrate it. Similarly, there is some space, some charges are uniformly distributed. For our case, it is non-uniform distribution here. For equation, they are very much tightly bound. The spacing between the charges is tending to 0. Then I will consider a small volume here, cube you can see. Here, say delta Q amount of charge is existing. Total charge is Q, total number of charges. But only in this part, I have got delta Q as the charge and volume is delta V. If that is the case, this is your charge density, volume charge density equation. If you want the overall density, then integrate it. This is about the charge density and the continuous distribution of charges. In force and in electric field intensity concepts, in the introductory parts, we have started with the point charge, then 1 charge, 2 charge, n number of charges. But if the same concept is extended to infinite number of charges, then this continuous charge distribution concept comes into picture. I hope you understood what are these charge densities. Any doubt here? Please, you can ask me. Any doubt? The doubt probably may be this one only, why we should go for delta. If the concept, it's a general tendency, even in your integrations you have done this, a smaller value you take, only for small portion you apply the concepts, For to get the complete answer, you integrate the terms. This is the general thing. Even in electromagnetics, throughout, whenever we go for any derivations, the one concept we apply to a smaller part, then we will extend the concept to the overall area what all we have considered by integrating the term. Any doubts? No doubts? Okay, understood. Fine. So let's move to the actual concept. I have not written the heading here. Please pardon me. Here I should have written the title. What is the title? You can see it. I'll just read it out. Field due to continuous volume charge distribution. This is the thing we have to find. We have in the previous session completed E, electric field intensity. Now we have to calculate this field for volume charge distribution, which is continuous in nature. Okay. Now, in order to go for this concept, it was very much necessary to understand what is uh, continuous charge distribution and what is charge density. That's why I took that concept. Now coming to your actual topic, the field due to volume charge distribution. Please, you can take the heading here, electric field intensity E due to volume charge distribution. Here in short I have written, it is visible hopefully, volume charge distribution derivation for E. Okay, this is the title. Let's move to the actual derivation. In order to derive, we should have the idea of continuous charge distribution and volume charge distribution. So we have studied just now in the volume charge distribution. Suppose we have some space considered. In that, say infinite number of charges are spreaded over, and how they are spreaded, they are continuous in nature, means very much tightly bound. The distance, the spacing between the charges is tending to zero. Okay, this is the distribution. In this, a small portion, in this a small portion I have considered, say point M. M is the point I have considered. And what is the amount of charge exists here? It is delta Q. Instead of capital Q, I have taken small q. Delta Q. And P is the point of observation where I have to find electric field intensity. And what is the distance? Distance between the charges present in the space M and the point of observation where we want field is small r. And this r cap is indicating the unit vector. Okay. This figure I have depicted here. Consider a continuous distribution wherein number of charges are infinite. Okay. And P is the point where we need to find electric field. Now let us consider a small space in which a very small amount of charge delta Q is present. This red square indicating the space considered. Okay. And point I have shown it here. It is M. M is the point considered. Now the distance from P to M is smaller. Okay, this is smaller. The same thing, the figure what we have considered, the same thing we have written. Okay, with this we know this already. What is E is equal to? Shall I show you what is E is equal to? Okay, E is equal to 1 by 4 pi epsilon naught charge divided by r square into unit vector. So the same thing, let us try to apply for our considered thing. E is equal to, now don't consider delta, I will tell you. E is equal to 1 by 4 pi epsilon naught delta Q divided by r square into r. Considered charge is delta Q. Okay. Now, why I have taken delta E? Anyone? Please answer me why I have considered in this figure, delta E. Why this triangle I have put as a delta? The charge is delta Q. Anyone? You can unmute and answer me. No issues. Why the electric field intensity is denoted as delta E? Why not directly E? What's the point in considering delta E first? Why not straightforwardly electric field intensity capital E? Okay, I have got one answer. Let me see. Small electric field. Yes, Misbah, it's very correct. See, we have not considered the complete charge, right? A small portion delta Q we have considered. Out of the whole space, a smaller portion we have considered, that is having the charge delta Q. Hence, the field will also be smaller, the only some part of the field, delta E. Okay, so hence the electric field intensity at point P due to only this amount of charge is delta is equal to this. Okay, now where r is the unit vector, you know it, delta Q is a smaller charge which is a point charge. Now as we are considering delta as the smaller charge, smaller means what? The distance between them is tending to 0, and they are somewhat, their point charges dimensions are tending to 0 point. You just show a point charge by a dot, right? So its dimension is also tending to 0. So tending to 0 means what? If I think you have studied this in your calculus, if anything limit, okay, if it is tending to 0, this del will become d, right? It is the difference, the changeover, what you say. Okay, let me give you one example. If suppose this is, you have studied this already, this is your signal u of t. Okay, what changeover is happening here? Here at the left side you don't have any amplitude, on the right side you have the amplitude 1 constant. Now if you observe at point 0 time 0, what is the amplitude? It is, you say that it is 1, but actually what is happening, there is a changeover from 0 to 1 here. Okay, change is from 0 to 1, so the difference is 1 minus 0, like that you get 1. It is not exactly straightforwardly you got 1, it is actually the changeover is happening from the amplitude 0 to amplitude 1 at 0. So you represent this by d by the differential difference sign. In the same way, here when you are putting some value tending to 0, when you apply the limit for it, delta will become d. The changeover from some value to 0, the difference. Okay, this probably you have studied, you have derived also. This del part will become d. Okay, hence what we have considered, delta, the smaller dimension, it is tending to 0, delta Q is equal to tending to 0, it is not equal to, okay, tending to 0, it becomes, this delta Q becomes dq, and field also, it is delta, it will become d. See, the changeover is from delta to d. Understand this, why we are taking delta to d, there is a changeover from some value to the 0. The changeover is defined or is depicted by this difference operation, okay, derivative d by. Hence the same equation we can write in this form. What is the change in both the equations? Delta has been changed, modified to d operation, d by. Okay, then this is a smaller field due to smaller portion of the charge, right? Only this point M, whatever area is covered, that particular delta Q is covered. So the whatever field is a smaller field. Okay. Now if you want to apply this concept to the throughout, whatever distribution is there, any number of charges, say you have q number of charges, earlier a smaller portion has delta q. So if there are totally q number of charges, if you want to apply this concept to the complete, you have to go for integration. Okay, so this is the smaller value of the electric field. But if you want to apply the concept and find the electric field intensity at point P due to complete charge distribution, the entire figure has to be taken into account, this whatever shape I have taken. For that, we have to take capital E as the integration of this. Whatever equation we got, you have to integrate it. Remember, a smaller portion we apply the concept to get the overall, part, the overall value. We go for concept extension by using the integration. Okay, this is a general thing we do. We apply it in many things. And even this integration, the same thing I have substituted here. You can rearrange the terms. This is a constant and this is the integration term. This is your equation 1. Okay, till this any doubts, please you can ask me if you have any doubts, else I'll move to the next. Any doubts still here? Unmute and answer me, no problem. The only important thing here is you should remember how this del has been changed to d. Okay, this limit when you apply, delta will become d. Any doubts? Shall I move to the next? Till equation 1, hope you understood. Using this particular figure, we have got this electric field equation E. Okay, shall I move? No answer. So either you have understood everything or did not understand anything. I did not get any answer. Till then, I'll continue. Let's see if anybody answers. If anybody has any questions, please put it in the chat box. This is equation 1. Okay. Understood. Okay. Tayyaba is telling understood. Let's see. Let's hope that it is applicable to all. I am integrating it. Equation 1, till now we have got this equation 1. Remember, I have not applied still this rho v concept. I am taking a small part. I have taken the small q. I have found out a small electric field, then applied to the complete portion. I have got the total E. But nowhere I have used this term rho v. Okay, now let us use the charge distribution, volume charge distribution, which is the heading concept. Okay, now we know that for the volume charge distribution, rho v is given by charge per unit volume, or if there is a delta q charge in a small volume delta v, rho v is equal to delta q by delta v, and the limit applicable is delta v tending to 0. And as I have told you just now, whenever it is limit application of delta tends to 0, some value to 0, there is a changeover, there is a difference of the values. Delta will change to d, d by dq by dv. So let us get dq from this equation. Dq is equal to rho v into dv. Let us substitute this in your equation 1. So the field, just now you have seen E is equal to integration, and this equation 1 I have rewritten. What is the change? I have used a small v. V indicates volume. We have applied the integration over a volume and put dq is equal to this from this above equation in the equation 1. So 1 by 4 pi epsilon naught this, and instead of dq substitute rho v into dv r square this. Or if you are using a continuous charge distribution and assume that if at all this is a constant value, then take it outside of the integration and remaining is this. Okay, this is the electric field intensity value for volume charge distribution. Okay, now what here I have written in the vector form, how we can write? Remember, till this is the same figure which is used here. See, both figures are same. Point M and point P are there, distance R, and delta Q and point M. The same figure, I have drawn it here one more time. See, point M is there, point P, and here I have taken origin O, because in order to find the values in vector form we need origin, right? As reference, we need 0 as a reference. So I have drawn two position vectors from origin to P and from origin to M. This is your distance vector between M to P. Now, in this equation, small r I have used, that small r is replaced by capital R, distance between M and P. What I have done? The same, this outside the integration constant, this integration is, I have written same, dv I have written same. Instead of r, I have to write this capital R. From the vector addition, apply the law of triangle here, vector addition. R plus R dash, same direction. See, continuity hai, direction. In the direction, there is a continuity. This plus this is equal to R, or capital R is equal to R minus R dash. I have substituted that. This R square is the magnitude, and unit vector is the vector, position vector's vector divided by its magnitude, and magnitude 2 and magnitude 1 I have clubbed together and put it as Q. This is uh, the electric field intensity due to volume charge distribution in vector form. However, this is the equation we got finally. If you want, you can present it in vector form as well. This is the concept today we completed: continuous charge distribution, then line charge, surface charge and volume charge densities, and then the derivation of the field capital E for volume charge distribution. Any doubts till now? Whatever we have completed today, please ask me if you have any doubts. Any doubts?